Welcome to part 3 of my video playlist about the preparation of benzonitriles. In this video I'll show you a number of procedures for the amoxidation of alkyl benzenes and benzylic alcohols or halides. Amoxidation is an oxidation conducted in the presence of ammonia, which yields nitriles or imines directly. Most industrial amoxidations are high-temperature gas-phase reactions catalyzed by various metal oxides. These reactions are assumed to proceed by initial formation of an aldehyde, followed by condensation with ammonia and final dehydrogenation to the nitrile. The optimal ratio of arene, ammonia and oxygen or air must be carefully determined to stay outside the explosion limits. Acrylonitrile, hydrogen cyanide, benzonitrile and various halogenated benzonitriles are the most important products prepared by amoxidation of alkanes. More selective amoxidations than the gas-phase version have been developed. In these two examples, instead of oxygen-ammonia mixtures, terz-butyl nitride was used both as oxidant and nitrogen source, and the oxidation was catalyzed by a mixture of N-hydroxyphthalimide and palladium acetate. This enabled both a high-yielding single amoxidation of metaxylene and the clean amoxidation of Bock-toluidine. Instead of palladium acetate, less than 1 equivalent of aluminum chloride can also be used to bring about this amoxidation. Again, the oxidation here proceeded smoothly in refluxing acetonitrile. In general, alkyl groups substituted with electron-withdrawing substituents, like the methyl groups in acetonitrile, acetophenone or acetone, are more difficult to oxidize and will react more slowly than non-deactivated benzylic methyl or methylene groups. Another variation is based on the copper-catalyzed amoxidation with diacetoxyiodobenzene as oxidant and sodium acide as nitrogen source. These reagents converted 4-ethoxytoluene into a nitrile already at room temperature, without any oxidation of the ethoxy group. Like the previous two examples, the required reagents are expensive if compared to mixtures of ammonia and air, and will only make economic sense if the target nitrile also is expensive and cannot be prepared by other strategies. Primary benzylic alcohols are easily oxidized to aldehydes and are therefore suitable starting materials for amoxidations. This is an example of amoxidation in toluene with manganese dioxide as catalyst. Toluene apparently did not undergo oxidation under these conditions. Like in the gas-phase amoxidation, the formation of explosive gas mixtures must be prevented, for instance by using air instead of pure oxygen or by diluting the gases with nitrogen. Also, the use of a less flammable solvent like dichloromethane or acetic acid or some flame retardant can be helpful to preclude accidents. In this example, the catalyst was a mixture of 5% of a copper complex and of tempo, and benzylic alcohols could be oxidized selectively in the presence of ethanol. Because of the flammability of ethanol, this procedure does not look safe, and either a less flammable solvent or diluted oxygen would be a better choice. Another strategy is the use of oxone as oxidant, as shown here. Only 3% of a nickel-copper formate mixture was enough to complete this amoxidation in only 1.5 hours at room temperature. No oxidation of the catechol or the solvent isopropanol occurred. Also, benzylic amines can be dehydrogenated to nitriles. In this example, 1% of a ruthenium complex brought about such an oxidation in refluxing toluene, without any stoichiometric oxidant. Benzyl chlorides are also more readily amoxidized than toluenes, as shown here. In this example, trichloroisocyanuric acid was the oxidant and the reaction was conducted in aqueous ammonia. There are several publications about the use of mixtures of ammonia or ammonium salts and iodine or electrophilic iodinating reagents for amoxidations. I won't show you any of these because I consider such procedures grossly negligent and extremely dangerous. Mixing ammonia with iodine can yield nitrogen triiodide, which readily sublimes and is a shock-sensitive explosive. Similarly, in the present example, nitrogen trichloride may be formed, which is also a dangerous explosive. At room temperature, however, it is a liquid and does not enrich itself by sublimation, like nitrogen triiodide. So be careful when mixing halogenating reagents with ammonia. Sodium acide can both function as oxidant and as nitrogen source for M oxidations. Here, a benzylic chloride was converted into a nitrile by treatment with a slight excess of sodium acide and catalytic amounts of a palladium complex. Even aryl acetic acids can be suitable starting materials for M oxidations. There won't be many instances, however, where such a transformation will make economic sense. But academic chemists often just want to know what is possible, no matter if it creates or destroys value. The madness of publishing as much as possible and anything is certainly also a reason for such oddities. The prices I've included are for laboratory samples, not for bulk quantities, but aryl acetic acids will almost always be more expensive than benzonitriles, no matter the quantity. Here, the M oxidation was performed with oxygen as oxidant and urea as nitrogen source, in the presence of 20% of copper trifluoroacetate. No oxidation of the unactivated methyl group occurred. The same transformation can also be achieved with an excess of sodium nitrite and iron triflate. Aromatic aldehydes and anylides remained unchanged under these conditions. The M oxidation of aryl acetic acids and alpha-aryl ketones proceed by conversion of the activated methylene group into a ketone or an oxime, as shown here. 1,2-dicarbonyl compounds or derivatives thereof readily undergo C-C bond cleavage, either thermally or upon treatment with nucleophiles. As you saw, there are many different strategies to perform M oxidations. Selectivity will always be an issue, and the unwanted oxidation of other functional groups will be one of the main side reactions to be expected. Then, because sometimes high reaction temperatures are required, hydrolysis of the product may also become a problem. Here are some more recent examples, including M oxidations with iodine and ammonia. For the reasons mentioned above, I would not try these, not even on a small scale. Like liquid diazomethane, nitrogen triiodide is often the last thing you see. The next video of this playlist is about the preparation of benzonitriles by electrophilic cyanation of unsubstituted arenes. This includes cyanations with electrophilic cyanation reagents, such as cyanogen chloride, and cyanations by radicals or through intermediate aryl halide formation. See you then.